There are a lot of numbers. That's easy even for the layperson to realize. Counting up 1, 2, 3, 4, 5, 10, 100, 1,000, a million, a billion, a Google, infinity perhaps. There is no end to the number of numbers, so we call that number of numbers infinite. But as the concept of what a number is evolved, so did the infinities of what we call our set of numbers. We'll start with the natural numbers, 1, 2, and 3, and on and on. The numbers adored by the Pythagoreans that made up their world. It's easy to define, at least at this point in time. Start at 1, then add 1 to get the next number. The natural numbers are identified with a fancy bold-faced n. As of yet, 0 hasn't been thought of, but when we add it to the set of natural numbers, we get the whole numbers, denoted with a W. The natural and whole numbers have a definite start, 1 or 0. Then you add 1 to get the next number. These are also known as the counting numbers because, well, we count on and on to get the next. To get the integers, we add the negatives of the whole numbers to that set. These numbers are denoted with a bold-faced Z. Well, at first having the negative of some objects made no sense at all. It was used for subtraction until numbers became abstract enough to be studied by mathematicians. Next, we have the rational numbers, which can be expressed as one integer divided by another. Rationals are denoted with a Q. These were the numbers known by the Pythagoreans and believed to make up the complete, continuous number spectrum. They were, however, proven wrong. Every other number that is not rational is irrational, and these make up the vast majority of numbers. The first of the irrationals, the most rational rationals, perhaps, are the constructible numbers. These are the kind of numbers you can find by measuring geometric constructions with a ruler. These include the square root of 2 and 5, the golden ratio. Next come the algebraic numbers, denoted with an A. These are all the numbers that can be written as the solution to some algebraic equation, such as the third root of 2. Finally are the transcendental numbers, non-algebraic numbers, the first of which are the computables, which, as the name suggests, are numbers that can be computed to an arbitrary degree. This includes e, pi, and only a couple more. Numbers that cannot be computed are the uncomputables. Only certain artificial numbers that we know of exist here, alongside normal numbers, normal from the point of view of a mathematician, that is. However, the numbers mentioned are only the real numbers, denoted R. The real numbers constitute the entirety of the continuous real number line, from negative infinity to positive infinity. Then, mathematicians decided to draw a line of 0, perpendicular to the real axis, to create the imaginary axis. Real numbers rotated 90 degrees. The imaginary numbers use the unit I, defined as the square root of -1. Adding the sets of imaginary numbers and the real numbers to create two-dimensional space, we create the complex numbers, denoted C. These numbers are of the form a plus bi, a being the real part and b being the imaginary part, or component. Multiplying these types of numbers can be defined as adding the rotations from the positive real axis and multiplying their distance from 0 plus 0i, the origin. Then, mathematicians got really clever. They figured, why not take the square root of I and negative I? They did, and as a result, we now have the j and k axes, 45 degrees from the real and imaginary axes, as the appropriate halving of the angles from projected. These new numbers are defined as a plus bi plus cj plus dk and are called the Quaternions, denoted H for their inventor, Hamilton, and represent four-dimensional space. Cutting to the chase, they did this again, producing the Octonions, O, and Sedenions, S, as well as dual numbers, which represent the infinitesimal. Now, those numbers are strange and are rarely dealt with in elementary mathematics. There are also numbers purely within the integers that interest mathematicians. There are the odds and evens, primes and composites. There are polygonal numbers that can be expressed by the number of the dots that make up a polygon. There are perfect numbers, where the sum of the prime factorization is equal to the number itself. Mathematicians love to group, even with a concept so simple as the continuous number line, which makes up all the numbers. And this discovery, or invention as you will, of new numbers turns out to be more practical than previously thought. As imaginary those numbers seem, complex numbers are commonplace in physics, as are quaternions in movement.